Unlike most ethers, epoxides are a special member of the ether class, which is extremely reactive. Before we get into the reactions of epoxides, let's cover how epoxides are made. Epoxides are three-member cyclic ethers, so they contain two carbons and an oxygen within a three-member ring. One of the ways we can make epoxides is by taking an alkene, adding MCPVA, which stands for metachloroperoxybenzoic acid. It is this molecule here. By adding MCPVA and an alkene, we can produce an epoxide, and it gives us a byproduct of metachlorobenzoic acid. The reaction is said to be a syn addition of the oxygen, in particular this oxygen here from MCPVA. Both bonds between the oxygen and the two carbons that used to be part of the double bond will be added from the same side. Therefore, it is a syn addition of that oxygen. Here is a look at the mechanism. It starts with the double bond attacking the outer oxygen, breaking the peroxide bond. So an oxygen to oxygen single bond is called a peroxide bond. So it's a very weak bond. Those electrons will be shifted here between the oxygen and this carbon. Then the double bond here, one of the pi electrons will be used to pick up this hydrogen, so that hydrogen goes to the oxygen. And then lastly, the electrons from the hydrogen to oxygen bond will be moved to attack the developing carbocation. That essentially leads to forming two bonds between the outer oxygen, so from this electron movement and then the last electron movement, those two bonds are created to the oxygen between two different carbons. And then once again, the byproduct is metachlorobenzoic acid. Another method to make epoxides is through an intermolecular Williamson ether reaction. In order to do this, we have to have a transhalohydrin. In other words, a molecule that has a hydroxyl group and a bromine or chlorine on the adjacent carbon. If we add base, such as sodium hydride or sodium hydroxide, we can remove the protohole, which would make it into a better nucleophile and allow attack on the carbon with the leaving group. That produces the epoxide. Here's a look at the mechanism. Sodium hydride would remove the hydrogen on the alcohol, put a negative charge on the oxygen. That turns the alcohol into an alkoxide. It's a much better nucleophile than an alcohol. Then that oxygen will attack the carbon that has the leaving group through an SN2 reaction and produce the epoxide. Now, you might be familiar with transhalohydrin. We have seen those before, certainly in Organic Chemistry 1, where we started with an alkene and we added Br2 or Cl2 plus water to produce the transhalohydrin. If we use Br2, we will get a bromine. If we use Cl2, we'll get a chlorine. Notice the product is trans and there are adjacent carbons. Here's another example of using a transhalohydrin to make epoxides. So starting with cyclohexene and adding Cl2 and water, we can make a transhalohydrin, followed by base, sodium hydroxide. It will remove the hydrogen on the alcohol, making a alkoxide, which is a much better nucleophile than the alcohol. The alkoxide will then attack the carbon with the leaving group to form the epoxide. Unlike most ethers, epoxides are extremely reactive. They usually undergo reactions where a nucleophile will open the epoxide ring. If we use a weak nucleophile such as water or an alcohol, Generally, we need to use an acid to first protonate the epoxide to turn the epoxide into a better electrophile. So for example, if we use this epoxide, we could use sulfuric acid to protonate the oxygen. Then water or an alcohol can add to the more substituted carbon through an SN1 type reaction. The water will generally add from the opposite side of the epoxide ring, so in this case from the bottom, and that is why this alcohol will be at the bottom of the molecule. In the process, any substituent like this methyl group will be inverted in stereochemistry, so it starts as being down, it will finish facing up. In the process, this oxygen from the epoxide will swivel over and become another alcohol with the same stereochemistry as the original epoxide. Here's a closer look at the mechanism for epoxide ring opening under acidic conditions by water. So if we mix sulfuric acid or some other acid and water, we'll make the hydronium ion, which can then protonate the epoxide oxygen. Then we'll have this intermediate, which will be attacked by water. If it's a symmetrical epoxide, it won't matter where the water adds. If it's a unsymmetrical epoxide, water will usually add to the more substituted carbon. In the same step, the bond between carbon and the oxygen will break and the electrons will be sent to the oxygen to eliminate the positive charge on the oxygen. In the next step, water or another base will remove a hydrogen from the water molecule that added to open up the epoxide, and that will result in a trans 1,2 diol. The ring opening of an epoxide should remind you of other reactions we have seen in the past. For example, an alkene reacting with bromine will result in a three-member ring, which we call a bromonium ion, since it has a positive charge on the bromine. This will be attacked by the Br negative, which is the leaving group on Br2 from the first step. That bromine will attack and open up the three-member ring. Similar reactions occur if we use Cl2. That leads to a chloronium ion, which will be opened up by a chlorine. And another similar reaction is the oxymercuration or alkoxymercuration, where a mercurium ion involving a three-member ring with mercury having a positive charge, which gets opened by water. Similar to water, alcohols will add to epoxides under acidic conditions. For example, methanol and sulfuric acid will lead to the acid-catalyzed ring opening of this epoxide. Initially, the oxygen of the epoxide will be protonated, and then methanol will add to the more substituted carbon through an SM1 type reaction, leading to this as a product. Notice the methoxy group is added to the more substituted carbon. It will be added from the opposite side as an epoxide ring, so in this case from the bottom. And the methyl group that was originally there will be inverted from being down to being up. And then the oxygen of the epoxide will be turned into an alcohol. Here's a second example. We have an unsymmetrical epoxide. If we add sulfuric acid and sulfuric acid and methanol, the methanol will add to the more substituted carbon, giving this as the product. Halides can also be used to open up epoxides. Hydrogen halides provide both an acid and a nucleophile in the same molecule. Here's an example with a symmetrical epoxide. If we add one of the hydrogen halides, it could be HF, HBr, ACl, or HI. The halogen will add to one of the carbons of the epoxide. It will add from the bottom side since the epoxide was originally up. and then the alcohol will end up on the top, since that's where the epoxide oxygen started. As a result, we end up with a trans-halohydrin from this reaction. The addition of hydrogen halides to unsymmetrical epoxides, the reaction will change depending on the exact substitution around the carbons of the epoxide. For example, if we have a primary and a secondary carbon, like shown in this first example, the chlorine of HCl will generally add to the least substituted carbon through an SN2 type reaction, giving us this as a product. However, when we involve a tertiary carbon or a secondary benzylic carbon, which are highly stable carbocations, the chlorine will generally add more through an SN1 type reaction and will add to the more substituted side to give us this as a product. Let's take a look at the SN1 mechanism that we saw on the last slide, with involving a tertiary carbon that is attached to an epoxide. Notice in this example, here we have a tertiary carbon, and here we have a secondary carbon in this epoxide. If we add HBr, the first step would be to protonate the oxygen of the epoxide, giving us a protonated epoxide intermediate. We can think of that protonated epoxide intermediate as having a partial bond broken between the oxygen and the carbons that it is attached to. If we think about having a carbocation or a partial positive charge on the tertiary carbon, based on what we know about stability of carbocations, we would say that that's a more stable carbocation than the alternative secondary carbon or carbocation that would form from breaking or partially breaking the bond between this carbon and the oxygen of the epoxide. As a result, the bromine generally tends to add to the more substituted carbon when it comes to an epoxide that has a tertiary carbon or even a secondary carbon that is also benzylic. In this question, we're going to look at two examples of an epoxide ring opening with hydrogen halide, HCl to be exact. We have an example here that has a primary and a secondary carbon. In the second example, we have an epoxide that has a secondary carbon and a tertiary carbon attached to the epoxide. In the first example, we have an epoxide that has a primary carbon and a secondary carbon. When we add HCl, the chlorine will do an SN2 type reaction and add to the primary carbon to give us this trans halohydrin. However, if we have an example where there is a secondary carbon and a tertiary carbon, the reaction will undergo more of an SN1 type reaction, and the chlorine will add to the more substituted carbon, giving us this as a product. Use strong nucleophiles, stronger than water and alcohols. We generally do the reaction under basic conditions. There's no need for an acid, since the nucleophile can add directly to the epoxide without needing to protonate the epoxide first. An example of such a nucleophile would be the hydroxide ion, which can come from sodium hydroxide or potassium hydroxide. If we add this to an epoxide, generally the hydroxide will add to the less substituted carbon in an SN2 type reaction. That would give us this alkoxide intermediate, which would be protonated by water or some other proton source to give us a 1,2 diol. If we use the conjugate base of an alcohol, like sodium ethoxide, similar reaction occurs where the nucleophile adds to the least substituted carbon through an SN2 type reaction to give us this alcohol that has an ethoxy substituent on the carbon adjacent to the alcohol. Here's an example with sodium methoxide. It will once again add to the least substituted carbon, giving us a methoxy substituent there. Notice the stereochemistry. It is facing down since the original epoxide was up. The oxygen of the epoxide eventually becomes an alcohol with the same stereochemistry as the epoxide. There are a number of nucleophiles we can use with epoxides, for example, hydrides. So lithium aluminum hydride can provide a hydride to add to the least substituted carbon in an SN2 type reaction. That will result in the more substituted carbon obtaining an alcohol from the epoxide oxygen. Grignard reagents can transfer an alkyl group, such as an ethyl group, to the least substituted carbon, as shown here. An organolithium would do a similar reaction. In this example, we're using a methyl lithium reagent that would transfer a methyl group to the least substituted carbon. Notice in each case, the Grignard and organolithium, the alkyl groups are always added from the opposite side as the epoxide, in this case facing down. The alcohol will always end up on the top side if we start with an epoxide that is facing up. Primary and secondary amines are really good nucleophiles that can add to the least substituted carbon from the opposite side as the epoxide, as shown here. Note that tertiary amines generally are not nucleophilic since they already contain 3 carbon chains. Adding a 4th group from an electrophile would mean that the nitrogen would have a positive charge, and generally this does not occur. We're looking at 3 more nucleophiles. Cyanide can act as a nucleophile to add to an epoxide on the least substituted carbon, as shown here. A thiolate ion can also add to the least substituted carbon through an SN2 type reaction. And an azide would have a negative charge on one of the nitrogens, can also add to the least substituted carbon, as shown in this last example. Epoxides have been used in a number of syntheses throughout the years, including in the synthesis of some beta blockers. Here's an example, starting with this phenol. If we add base and an alkyl halide, we can do an SN2 type reaction where the oxygen attacks this carbon and eliminates the chlorine to attach this carbon chain that contains an epoxide at the end. If we add an amine to that epoxide, it will attack the least substituted carbon to give us our final product. In this question, we're going to try to predict the product from a Grignard reaction on an epoxide. Here we have an epoxide that has a carbon with 1 alkyl group, and this one has 2 alkyl groups, an ethyl and a methyl group. Grignard reagents are generally very strong nucleophiles, so they will prefer to do an SN2 type reaction on epoxides, and they'll add to the least substituted carbon, which is the carbon on the left. As a result, we have now the phenyl substituent on that carbon. The more substituted carbon will obtain an alcohol from the epoxide. In this slide, you'll have a number of questions, problems related to the reactions of epoxides. So I encourage you to try these reactions and try to predict the product from each of them. In the first example, we have an alkyne that has a negative charge. We know that since it's next to the sodium. And that carbon of the alkyne should attack the epoxide as a nucleophile. Notice this is an unsymmetrical epoxide. And you want to look at the possible products from this list on the right and pick the correct one. You try to solve the questions from the last slide. You should hopefully get the correct answers and you'll be able to answer The question was the sodium atom certain that he had lost an electron. The answer is on the bottom of this, but you will fill in essentially the letters that correspond to the products that were on the previous slide on the right side.